Alright, more math. Let A be the integers, m is z mod mz, n is z mod nz. If you take any alpha in M, let P alpha be just an abelian group generated by two elements E1 and E2, such that m times E1 is 0 and n times E2 is alpha times E1. Verify that we can make a natural short exact sequence. We'll call it fancy E alpha. So, and this will go from 0 to m to PA, or P alpha to n to 0. So, now it's not exactly clear what natural means here, but I'm just going to assume that natural means like just something that, like the first thing that you would think of. So for example, define a map phi. So phi will be going from m to p alpha. And where are we going to send phi of 1? Well, it's got to have order m, since that's the only way for this to be well defined. And so let's say phi of 1 is E1, because E1 has order m because of this property. Alright, since 1 generates m, extend this linearly to all of m. So now observe that phi is well defined, because if I and j are equal in m, that means that there's some integer such that I is an integer multiple of m plus j, and we have phi of j is j times e1, which is, we could write this as j times e1 plus mk e1, because m is 0 in, or because m times e1 is 0 here, and because this is abelian, you could blah blah blah, whatever. So this is just j plus mk times e1, and this is just I, and that's phi of I, so phi of j equals phi of I. So it doesn't matter which coset representative we choose. Certainly it's linear, because we defined it by extending it linearly. Lastly, if phi of j equals 0, then j e1 equals 0, so j equals m. This is a 0 element in M, so therefore the kernel is 0, which means that phi is injective. So that's part of what we want for a short exact sequence, is we need this map to be injective. Alright, now we want to map from P alpha to N, so we got to figure out where it sends E1 and where it sends E2. Let's say E1 should go to 0, because that way multiples of E1 will be 0, and multiples of E1 are what we get from here, and that's how we're going to get the image of phi is equal to the kernel of psi. So psi of E1 is 0, and psi of E2, let's say it's 1. So then extend it linearly to P alpha. Then psi is linear by construction. I guess first we should technically prove that's well defined. Certainly it's going to be 0. It's psi of 0 is 0 by linearity. Therefore, using linearity, well, maybe it doesn't matter that we did linearity first. So one thing that we could do for linearity is say that psi of 0 equals psi of me1 equals, okay, but again we're using linearity here, because the way that we define m times e1 is just as this m times psi of e1, which psi of e1 is just 0, so it's m times 0 equals 0. So yeah, so then, well, why do I have this here then? That's this is very circular feeling. So we'll write this. this, that. So furthermore, psi of n times e2 is, well, you can factor out the n, and then that's just n, and n is 0 in capital N. But this is alpha times psi of e1, because psi of e1 is just 0, and of course we can bring the alpha inside. So yeah, this confirms that the relations that define PA blah blah blah, thus it's well defined. Next, psi is surjective because given any n prime, psi of n prime e2 is you just bring it's just it. Okay, so it's surjective. Therefore, the last thing we need is for the image of phi to be the kernel of psi. For this, take some element in the image of phi, then there is some x such that phi of x equals y, so y equals x times e1 because that's what phi of x is. Then psi of y is psi of x e1 because that's what y is, and we can factor out the x, and psi of e1 will be 0, so this is 0, so y is in the kernel, therefore the image is contained in the kernel. Now for the reverse inclusion, take y in the kernel, that means psi of y is 0, P alpha is generated by e1 and e2, so we can write as y as some linear combination of e1 and e2. Then psi of this linear combination, you just use linearity, but this is just b, and since psi of y equals 0, right, since psi of y equals 0, this means that b must be 0. So if b is 0, then y must be just a times e1. So choose some a prime in M, which is congruent to a mod M. And do we have to do that? Yeah, because we don't really know, because a is in Z. So because we don't know where in Z it is, we want to get an element which is in the same M coset of A. So we'll call it A prime. Okay, so ME1 is 0 in PA, and we have phi of A prime equals A prime E1, because this phi of A prime would be, wait, what? Oh, right. So phi of A prime is A prime times E1, but this is the same as A prime times E1 is the same as A plus Km times E. So this is equal to A plus Km times E1 for some integer multiple, for some integer K, because k times m times e1, m times e1 is 0, so k times m times e1 is 0. But this k is chosen such that a prime equals a plus km, and that exists because they're congruent mod m. And so then this is going to equal, okay, no, this should be a prime. And then a prime plus km is equal to a, so this is a times e1, and thus y is a times e1, and a times e1, well, that's just the image of some element of m, and thus it's in the image of phi. Therefore, the kernel is contained in the image, and so the image is equal to the kernel, and therefore this is a short exact sequence, because we've proven everything that we wanted. We've proven that phi and psi are both linear maps. We've proven that that phi is injective, psi is surjective, image of phi is kernel of psi, and that's all we needed, and so we are now done.